Okay, welcome back everybody. We're finally going to finish section 5.5, which is also the end of chapter 5. So we're basically finishing everything with regards to integral transforms and spectral theory. And I'm titling this Applications of the Spectral Theorem. Let's just recall where we ended. We basically ended by stating that we can construct a Green's function for a Hermitian operator. Recall Hermitian just means that it doesn't matter which side of an inner product an operator acts on, you get the same value. You can construct Green's functions for those by finding their eigenfunctions and then performing the following summation, where you sum over all of the eigenvalues. You take the 1 divided by the eigenvalues, the reciprocal eigenvalues, and then multiplying the eigenfunctions in the variable y with a complex conjugate against the eigenfunctions in the variable x. So when you perform that summation, you recover a Green's function. What we're going to do in this section is we're going to actually develop the Green function for two cases of the Laplacian. Now, the Laplacian tends to be the most common operator that we use for these. That's because of Green's identities that says it is very often a symmetric operator. So we want to think about symmetric operators often being like the Laplacian on some sort of domain where the boundary vanishes. So either the boundary is empty or the functions take the value 0 on the boundary, or perhaps periodic or something like that. So here we are going to start with something called spherical harmonics. And to develop these, we are going to consider the Laplacian on C infinity of boldface S2. So this is the math blackboard S. So what do I mean by this math blackboard S? I'm referring to the sphere. So the sphere with a two-dimensional surface, which is just your three-dimensional ball, the one that everybody knows and loves. There it is, a three-dimensional ball, and I'm looking at the surface of that ball. So that is the two-sphere. It's defined in R3 as the set of points where x squared plus y squared plus z squared is 1. Just think about it as your favorite surface of the three-dimensional ball. So the question is, how does this differ from the two-dimensional torus, right? Because if you travel in 2 pi rotations in any direction on the two torus or the two sphere, you end up where you started. Two sphere, by the way, is just like the surface of the Earth. I don't know why I didn't start with that. The two torus, you'll recall, if we jump all the way back to section 4 or chapter 4 in the book, the two torus was really like this donut-shaped object where it kind of looked like that, and it had, was the donut. Do it like this. There you go. There's your three-dimensional donut. So the surface of the three-dimensional donut is definitely not the same as the surface of the Earth. These are fundamentally different objects. But they do both share the property that if you travel in 2 pi degrees in any direction, you end up where you started. It's just that you cannot contract loops to single points in the torus, right? A loop around one direction or even a loop around the center. You can't contract that loop any farther. But on the circle, on the surface of the Earth, all you have to do is move your loop upwards and you can contract it, right? If I had a rope around the equator, and for some reason I gathered up the entire rope and moved it all the way to the North Pole, then I could fit it into a box. But if I tie a string around a donut, no matter where I move that string, there's no way that I can put it into a box. So that's kind of the difference between S2 and T2. And we saw that the Laplacian with T2, I mean, we didn't necessarily derive this, but you could derive that that's just going to give you the two-dimensional Fourier series. If you act, Laplace on C infinity of T2, kind of the C infinity of the torus, these are the Fourier series. And so the two-dimensional torus just gives you the two-dimensional Fourier series. If you work on S2 instead, we're going to get something different. So what are we going to get when we look at the Laplacian on S2? When we calculate, we're looking for a Green's function, right? So that's kind of what I started this out with. We're looking for a Green's function of this Laplacian, meaning the Green's function that represents delta inverse, the inverse Laplacian. The way that we're going to do it is with spectral theory, right? We're going to be looking for, so we seek to solve the eigenvalue problem for delta. And what does the eigenvalue problem look like? Delta phi equals lambda phi, and phi is in C infinity of the two-dimensional sphere. So that's our eigenvalue problem. We're going to try to solve it. It's going to be to our advantage. Rather than writing the Laplacian as the sum of the squares in the x, y, z directions, we'll give ourselves no longer Cartesian coordinates, but spherical coordinates. Not really a surprise there. If the sphere is, symmetric under those coordinates, it's not really symmetric under the x, y, z coordinates, right? The x, y, z coordinates wants you to create a box. It's a very boxy coordinate system, not a very spherical coordinate system. So let's transition into the spherical coordinates. And this kind of goes back to Calc 3. I don't really expect many of you to remember this, but you can write the Laplacian, right, underneath a coordinate transformation, you just calculate the Jacobian and see what all the terms of the Jacobian are in each of the directions that you're calculating derivatives in. And you get that the Laplacian on the sphere looks like the following. Okay, so it cares about this variable theta. That's kind of my, let's recall that theta is this direction. And so theta can go up to 2 pi, start at 0 and go to 2 pi. And then in spherical coordinates, phi is this direction, and it goes from 0 to pi. So there's phi and theta. And of course, why isn't r showing up? Well, because I'm on the sphere, r equals 1. So normally there would be some, partial r terms in the Laplacian, but because I'm on the sphere, all of those have disappeared because r is equal to 1 on the sphere. So that's what my Laplacian actually looks like if I restrict myself to the sphere. And so I'm going to solve the eigenvalue problem where, the PDE operator actually takes this form. It's going to make it a little bit more clear how I'm going to solve the eigenvalue problem. So let's go ahead and, if we're going to find Green's function from eigenfunctions and eigenvalues, then I do need to set up and solve the eigenvalue problem. So let's do that. Set up the eigenvalue problem. I'm using capital Y here. This is just because it's common with the spherical harmonics. This is the literature name for the spherical harmonics is a capital Y. So that's the only reason I'm using capital Y here. But there's my eigenvalue equation, and then let's just recall what it would mean for Y, capital Y, to be in C infinity of the 2 sphere. That just means that 2 pi in the theta direction gets me back to where I started. That's what that line says. And 1 pi in the phi direction gets me back to where I started. Okay, so this is now going back to where I was saying we have to use separation of variables because we're looking for these in closed form. So we do encounter my least favorite part of PDEs and my favorite part of PDEs. Let's just put up with it. So we're going to follow separation of variables, and we're going to try to solve this PDE, which keep in mind the delta there is actually this. We're going to try to solve that with separation of variables. So I'll do that. I'll make the ansatz, which says that capital Y is actually capital theta. That's going to be my solution in the theta direction, times capital phi, which will be my solution in the phi direction. If I make that ansatz, right, I'm acting this version of delta onto that product of theta and phi, and we end up with this equality, right? So I'm getting 2 derivatives on theta, 1 derivative on phi, and 2 derivatives on phi. That's because of the product rule going on there. So you have a combination of 1 and 2 derivatives in the phi direction. And then that's always going to be equal to the eigenvalue equation, so just a multiple of theta and phi. So that is what the PDE turns into if I make the ansatz. And then, as always, with separation of variables, end of part 2, you choose a variable which you're going to solve everything against. So let's solve every term with the theta to the left-hand side. And I just brought the negative over because you've got to put the negative sign somewhere. I'll bring the negative over to the left-hand side. It means everything else on the right-hand side is just in terms of phi, as we can see, as well as lambda, right? Because technically lambda is sitting there as the eigenvalue. So everything's in terms of phi and lambda on the right-hand side, and because of the way separation of variables works, since everything on the left-hand side is a different variable than everything on the right-hand side, they both must be equal to a constant. I'm going to give the name constant mu squared. Keep in mind, I always like to make it a squared because we are in second order. So since we're working with a second order, really ODE now, I want to make it mu squared, and that just makes my second order solutions look a little prettier. But if mu is an undetermined constant, mu squared is also an undetermined constant. So there's not really anything we're losing by choosing mu squared. What that means is that each side, though, is independently equal to mu squared. So we're just going to isolate, we're going to separate right down the middle there and look at this mu squared term, and we're going to look at this mu squared term. That's going to give me 2 separate ODEs, especially if I rearrange them. So the ODE on the left looks like theta double prime plus mu squared theta is 0. And then the ODE on the right looks like phi double prime plus cotangent phi double prime, plus lambda, there's my eigenvalue, minus cosecant squared phi times mu squared times capital phi is 0. So what do we have here is we have this should be a single derivative, by the way. What we have is a second order linear constant coefficients problem. That's super easy to solve. The second order non-constant coefficients problem will be definitely trickier for us to solve. So constant coefficients, love solving that one with our exponentials. In this case, we have im and negative im. Why is there an m there and not a mu there? Well, I just decided to replace mu with m. This is, once again, to go back to the literature. When we have literature versions of the spherical harmonics, they often occur in terms of L and M. Those are the Roman alphabet conjugates to the lambda and mu that we already had in the Greek alphabet. So that's why we've got L and M there. They're kind of the conjugates in the Roman alphabet. And actually, L and M have to stick around in the integers and the natural numbers now. But the solution in theta is just exactly what you'd expect, because you're just constructing the characteristic equation out of that and then solving for mu, which is now m, and you just get im for both of the solutions of the characteristic equation. So That's going to be theta, not too tricky. The trickier one is here in phi, right? So what is the solution here in phi? Keep in mind that's just a single derivative. That, it doesn't look like it, but this is actually the Legendre, if I can spell Legendre polynomial equation in the quote-unquote variable cosine of phi. So if we go all the way back to the Legendre polynomials that we studied in section 5.4, there's a reason I introduced them. I introduced them because these are going to show up now when we do separation of variables for a PDE problem. So Legendre polynomials in the variable cosine, so you need a change of variables inside of that equation. But then you pick up the equation we have here, and technically the Legendre version is without the eigenvalue lambda there. So when you include lambda, you get something called the associated Legendre polynomial. So it's just a slight modification of the Legendre equation. But so that's why we had the Legendre polynomials from earlier show up. That's why I wanted to introduce them. And you find out that the solutions in phi look like this, right? The solutions to the Legendre equation, technically the associated Legendre equation in the unknowns L, right? So that's where my eigenvalues are, and then as well as the unknowns M. Those just show up in the Legendre equation itself as the m squared or mu squared. So that's how you actually solve for this phi. I mean, I'm not going to go through the work. It's not the easiest thing to do. Once again, you just make the change of variables, you get the original associated Legendre polynomial equation, and then do a power series method. So the way you find these associated functions is the exact same. Unfortunately, it's a little bit tricky to do that, so I'm not going to go through it all the way, but these are our solutions. If you care a lot more about them, go ahead and Wikipedia associated Legendre polynomials, and you'll see a derivation. And what we get then is, right, we made the separation of variables ansatz, so our actual solution is just going to be those two equations, or those two solutions in theta and phi multiplied together. So our actual solution will be the multiplication of theta here and phi here. Now, why did I make the specific choices? Right, so I did decide to reduce to a specific choice of lambda being L times L plus 1 for L in the natural numbers, as well as mu being M for specifically only the M's and Z. This was to make sure that my boundary conditions were met, right? Because I'm on the sphere, I definitely need that, theta at 0 and theta at 2 pi are the same. This is why the mu's were basically forced to be integers. We need integer multiples of 2 pi to satisfy periodicity. And then similarly in phi, this is where we need L and L plus 1. That's just because of the solutions of the Legendre polynomial equation, right? This is, if you go back to section 5.4, when I introduced the Legendre polynomials, this is just what we had to have to make those work. So all of a sudden lambda gets reduced to L times L plus 1 and mu gets reduced to the integers. So that's why we have those specific terms there, which means that when we reconstruct y, we have a sum over all mu's, because mu wasn't our eigenvalue, only lambda was the eigenvalue, or L in this case, and then we just multiply all of our terms together. So that's technically the solution if you go with separation of variables. Now, what we actually do when we develop the spherical harmonics is we say, by the way, these are actually that times this and this times this, or either of them times this, are all individually eigenvectors, they're eigenfunctions, because you could just make a choice on specific cases of C1, C2, D1, and D2. The whole thing overall was an eigenvalue solution, but independently, how many linearly independent basis functions do we have here? We really have this times this, this times this, this times this, and this times this. So we have 4 different basis functions. What we do is we look at the real versions of those, right? When we look at the real versions of the basis functions, we can restrict them to these. So these are really the real basis functions from above. And these are known as the real spherical harmonics. So if we just isolate the real versions of everything above, we get the real spherical harmonics. What do they look like, right? These are functions of theta and phi. What do they look like if I plot them? Well, what I should say before I show you the pictures is, if you've taken a course in chemistry, do the following structures look familiar? So here they are if I plot them, and I'm just going to throw some letters here to help you out if you've taken chemistry. Maybe those letters will jog your memory on what I'm referring to. And so it turns out that purely looking at the eigenfunctions, right? These are the eigenfunctions of the Laplacian on the sphere. Well, and these aren't all of them. These are the first. How many do I have here? I've got 7 plus 5 plus 3 plus 1. 16. These are the first 16 of them. Eigenfunctions of Laplacian on the sphere. This is actually how you find electron orbitals. So mathematically, the electron orbitals are just defined for us by eigenfunctions of the Laplacian on the sphere. This is what quantum mechanics has given us. It can predict the structure of atoms just by, performing some mathematics. And these actually determine how many elements are in each row of the periodic table. This is maybe a topic for a physical chemistry course, but I like to include it here anyway because it's pretty fun. Because we have 2 electrons per each of these orbitals, we multiply the number of these that we have by 2, and we see that there's a total of 2 cases in the first row. And then we multiply the number of basis elements in P, which there are 3 times 2 because of 2 electrons. We have 6. Second row, but we actually end up having a larger version of S, right? So we actually have 6 plus 2 second row elements. And then in D, we multiply by 2. We have 6 plus 10. We have 10 from D, and then 6 from the P, and then 2. Now in the fourth row. And then 2 rows later, we get to the lanthanide and actinides, and we have 14 plus 10 plus 6 plus 2 in the 6th row. And this would continue until you fill rows up. So purely mathematically, we can actually construct the periodic table just by solving these eigenfunctions, the Laplacian on the sphere, which I think is a very, very fun fact to know, especially if you've taken a PDE's course, but certainly it should be covered in a physical chemistry course as well. You just maybe don't actually realize that you can solve these ODEs and that they're referring to eigenfunctions. Okay, that was a bit of an aside, too much fun to not include. So the entire point of the example is to produce a Green's function. So, why would I go through all the work? That's to make a Green's function. So what do I do to create a Green's function? Well, when I've got my 2 independent variables, they need their 2 conjugates, and I'm just following proposition 5.5.13, right? That's the one that I introduced right away. So what we do is we take the basis elements, right? We take the eigenfunctions, which form the basis, and we take them in the conjugate variables, we multiply them by them in the variables that are actual arguments, and then we finish by summing over all of the eigenvalues. So here's me summing over all the eigenvalues. Technically, this is lambda inverse, right? So lambda was equal to L times L plus 1, so when I put that in the denominator, that's lambda inverse. Now this n that you see sitting around is technically a normalization constant, so you do need to make sure that the eigenvalues are orthonormal before you decide that you're going to construct Green's functions, so you do have to normalize them. We're not going to go through that work here. I just want to show that you can actually construct a Green's function for this problem, which means now that we have a Green's function, we can solve this. This is the arbitrary inhomogeneous Laplace's, well, it's technically Poisson's equation. Basically, the inhomogeneous Laplace's equation, the Poisson's equation are the same thing, on the sphere. So we can solve it on the sphere, no matter what f of x is, or f of theta and phi is. We just use exactly a Green's function formula, right? So now that we know what the Green's function is, there it is. We compute it. Since we've computed all of these spherical harmonics, you compute the Green's function, and all of a sudden you can solve an arbitrary inhomogeneous Poisson's equation on the sphere. So that's really what we get out of this final section in the book, is the ability to construct Green's functions just by solving eigenvalue problems. And let's move on to the second example, which is the vibrations of a drum head. And so here we're actually going to still work with the Laplacian, but instead of working with the Laplacian on the sphere, let's work with it on the disk. Right, so we got a circular drum head, there's my xy plane. I'm just going to be thinking about how does the Laplacian behave on the disk itself. So there's my domain, x squared plus y squared equals 1. It should just be less than 1 actually, that's the disk. X squared plus y squared is less than 1 is the disk, so you can think about it as a drum head. And we are going to make sure that all of our functions that the Laplacian acts on achieve a 0 on the boundary. Okay, that's what the subscript 0 means. It means that we achieve the value 0 on the boundary. That's pretty important, otherwise we're not going to be Hermitian. So we do need to verify lambda delta is Hermitian. And that's what this 0 on the boundary means. So it does have to be Hermitian. And then we're just going to solve on this domain, which is the disk, the 2-dimensional disk. Now, as before, it's not to our advantage to work in the xy coordinate system, the Cartesian coordinate system. It's to our advantage to work in the r theta coordinate system. This is a polar, right? It's a polar defined region because it's symmetric underneath rotation. So we're going to want to work in r and theta, in which case delta takes the form r inverse partial r times partial r plus r to the negative 2 times partial theta squared. So this is once again going back to Calc 3. You have to compute this underneath the Jacobian of this map from one coordinate system to another. But once you do that, you do recover a form of delta in terms of r and theta. And you can show that that's Hermitian just by Green's identity, right? That's why we had 0 on the boundary. So what we're going to do once again is try to solve the eigenvalue problem. which means we need to construct the eigenvalue problem, which we do right here. This is the eigenvalue problem of the Laplacian with respect to the disk, right? So with respect to the disk, taking the value 0 on the boundary, what have I done here? I said, oh, there it is. It takes the value 0 when r is 1. That would be the radius being equal to 1. That's the boundary itself. And what do I know about disks? If I rotate by 2 pi, I end up where I started. So that's the boundary conditions of the Laplacian, eigenvalue Laplacian equation on the disk with 0 as a boundary. And we're just going to try to solve this for arbitrary lambda. As before, we do have to resort to separation of variables, which means we make the ansatz that u, the solution to this problem, takes the form r, capital R of r, and capital theta of theta. So it's a multiplication of functions in each of the directions. And then what we do is we use, this version of the Laplacian in our PDE, since that's the polar version of the Laplacian. And under separation of variables, we get this. So you just go ahead and compute the polar version of the Laplacian on your separation of variables ansatz, and you get what I've just circled. We can rearrange, separation of variables still in step 2. You always need to rearrange for one of the variables. We'll just choose theta again. This gives us capital theta double prime over theta is r squared r double prime over r plus r prime over r plus r squared lambda. But once again, the left-hand side and the right-hand side depend on completely different independent variables, so they both must be equal to the same constant, which doesn't depend on those variables. This gives me 2 ODEs. Now that I have 2 ODEs, here's one of them, here's the other, or if I solve it in the form that I want to see them, that looks exactly like theta did before. Now my terms in r are going to look a little different than what they did before, right? So my terms in r here, that's, if I replace this with x, and then x, and then x, and I forget about the mu here, this is exactly Bessel's equation. So back in section 5.4, when I talked about the Bessel functions as solving Bessel's equation, there's a reason I did that. And so we have Bessel's equation here, which is the shape that the drum head's going to take in the radial direction. And then as always in the theta direction, we're just going to be periodic. So we know what the periodic solutions look like. These are the complex exponentials, or you can equivalently think cosine and sine. And then the Bessel functions show up solving my Bessel's equation. So we end up having Bessel functions in the variable r. Now we do have to comment here, right? Because I'm letting lambda be alpha mn squared. What the heck is that? Alpha mn squared, there I'm making it show up in my Bessel function. So alpha shows up in Bessel function. What is it? It is the nth positive root of Jm. Okay, so if we jump back to section 5.4, you'll recall that these Bessel functions kind of look like this. So it has a first positive root, it's got a second positive root, a third positive root, and so on. So it's got a bunch of these positive roots. We're just going to enumerate the roots. This is like alpha 1, alpha 2, ... So we enumerate those and we just add them into j. This is to guarantee that when r is 1, j of alpha times 1 is just j of alpha, and this has to be 0, right? And this is because we want to achieve 0, value 0, when r equals 1. Okay, so that was kind of a restriction of our boundary condition, right? And so we're going to include that in the Bessel functions. And then the separation of variables says our solution is just theta times r. And so we go to our solution, it's theta, there's theta times r, there's r. And as before, there's really actually multiple basis functions going on. There's that and that multiplied by that. So there's going to be some real versions of this, which we can make. We can form the real versions as cosine times the Bessel function and sine times the Bessel function. And we can look at what these actually look like. So here's kind of the first 4 cases. What do you know? That looks a lot like a drum head vibrating. So you can imagine if I hit a drum right in the center, that's what I get here. This is like the 1-1 case, maybe even the 0-1 case. Or if I hit it in the center a little bit harder and get a taller spike, I could get this, which is like the 1-2 case. If I hit it a little off center, maybe I hit it right here, it's like the 2-1 case, or really hard off center, like the 2-2 case. And so depending on which, how much energy I impart to the drum head and where I hit it, I'm going to recover a different shape. And so these are the harmonics. These are called disc harmonics, or most people do just call them vibrations of the drum head or modes of the drum head. But we can purely, with PDEs actually construct what these should look like. And that's not really the point. What was the point? The point was to construct a Green's function for the Laplacian. So now that I've found my basis functions, separation of variables. I realize I kind of skipped over choosing lambda and mu, but just as before, you just choose lambda and mu as the numbers that they have to be, the only ones that actually solve the problem with the boundary conditions. So once you translate lambda and mu, you can actually construct the Green's function as we did before by summing over all of the eigenvalues. There's lambda inverse, right, my denominator. Here's one of my basis functions in the variables rho and omega, and then my second basis functions in the variables r and theta. This is just coming straight out of proposition 5.5.13 once I've found all of my eigenfunctions and eigenvalues. So now I have Green's function, and that means I can always solve this Poisson's equation. Since I've found Green's function, I can solve Poisson's equation. So there's just my second example. There's my solution to Poisson's equation, just by definition of the Green's function. And that's really how the spectral theory gets used, right? We're always going to start with a Hermitian operator. We're going to find all of its eigenvalues and eigenvectors, and once we do, we can construct the Green's function out of them. That's the whole point of the spectral theorem, is really to help us find Green's functions, and in fact to find some other related functions of the operator. So I did want to add this really quick. The eigenvalue equation for the Laplacian does have its own name. It's called Helmholtz's equation. So you'll see that in physics periodically. Somebody will refer to Helmholtz's equation as the eigenvalue equation of the Laplacian. And then I have a pretty quaint remark here. It's called, can one hear the shape of a drum? Which goes back to this 1966 article by Mark Catch, in which he asked the question, knowing a Laplacian is acting on a space, and suppose that we have the point spectrum of the Laplacian. So suppose that we know we have a Laplacian and its point spectrum, but suppose we don't actually know the shape of omega, right? So don't know the shape. No shape omega, but we do know point spectrum. Can we determine the shape, right? So is there some unique correlation between the point spectrum and the shape? Turns out the answer is no, for the reason that these two omegas that we have in front of you actually give you the same point spectrum. You interpret this as, is it possible to hear the shape of a drum? Because if you were to take a frequency analyzer and you hit the drum, you could see all the frequencies show up. Those are exactly the point spectrum. So you would see all the frequencies show up, and that's your point spectrum, and you'd be like, okay, so I'm just going to assign the point spectrum a shape. But unfortunately, there are these two shapes, which have the exact same point spectrum, but they do not clearly share a shape. There are some restrictions in which it's true, though. So that's just kind of a quaint remark. I think it's kind of cute to include it in this section, even though I guess it's not the most important thing to cover. It's a nice thing to know. And then we're going to finish section 5, chapter 5. It's great. With the functional calculus. So this kind of goes back even to kind of section 4.2, I believe, where we talked about the Fourier multipliers and the Fourier functional calculus. You can define a functional calculus for Hermitian operators as long as they admit, their nice spectral decomposition. So that's a spectral theory associated to L. You define an entire class of operators called f of L, or the functional calculus of L, just by taking f of the eigenvalues. Okay, so you're going to replace the multiplier of lambda, multiplying by lambda with multiplying by f of lambda, right? So some function, whatever function you want, as long as it's defined on your point spectrum, you just multiply by that function instead of multiplying by lambda. Now you have a brand new collection of operators that you can define. This is actually pretty important, right? This is what we did with the heat and the wave equations by defining e to the TL. So this is just the decomposition of L, but now with an e to the t lambda in the middle, or e to the plus or minus t L to the 1/2 is the same thing. You decompose it, but you replace lambda with e to the plus or minus t lambda to the 1/2. And so these actually satisfy the generalized heat equation, right? This is really the heat equation for L, and they also satisfy the generalized wave equation. This is the wave equation for L. So you all of a sudden gain like a brand new perspective on heat and wave equations. You don't need the Laplacian on the right-hand side. You can work with any Hermitian operator, L, on the right-hand side. So this is what the functional calculus gives us the ability to do. Anyway, I'm going to stop there. It's probably the longest video of these three. This section's insane, but it's really cool. I really, really appreciate all these results. I hope you do too. And we'll move on to the Cauchy-Kovalevskaya theorem in the next video. See you then. Bye.